Students, good morning.
Very good morning, sir.
Good morning, sir.
Good morning, sir.
So nowadays we are discussing this calculation of entropy changes in different types of processes. So yesterday we have derived an expression for calculation of entropy change for an ideal gas whenever there is change in pressure, change in volume, and change in temperature. And conclusion of the discussion, or you can say the final expression for this entropy change was equal to delta S. Delta S was S2 minus S1, and this was equal to Cv times integration from T1 to T2 dt by T plus R and integral V1 to V2 dV upon V. So this equation consists of two terms. One corresponds to the entropy change contribution due to change in temperature, that is the very first term. And the second term, this is due to the change in volume of the gas during expansion. So this formula holds good whenever our gas is expanding or compressing, and during expansion or compression, what is happening? Temperature change is also taking place. Now we can also simplify this formula as delta S is equal to Cv times ln T2 by T1, because this integration of 1 by T is equal to ln T, and if we substitute upper limit and lower limits, so we will be having this expression Cv times ln T2 by T1. Similarly, in the next term, we will be having R times of ln V2 by V1, means final volume divided by initial volume, and natural logarithm is to be taken for that. Now this formula or this equation number I think 42, so this holds good if we are having only 1 mole of gas that is uh, expanding or compressing. In case we are having n number of moles of a gas, then n will be appearing with both of the term, and we will be having delta S is equal to n times Cv ln T2 by T1 plus nR ln V2 upon V1. Now, if we look into this equation number 43, so from this equation, it is evident that the entropy change means delta S, that is taking place during this expansion, compression, during which this temperature change is happening. So this entropy change for the change of the state of an ideal gas, this has to depend upon the initial and final volume. Means in this formula we are having V2 V1 means initial final volume, and in addition to this, it is also depending on the initial and final temperature of our gas that is under consideration. Correct? So this is general formula that we would like to apply in case both of these parameters are changing, and during these changes what happens to entropy. So this formula holds good. Now this expression we have derived keeping in mind that volume as well as temperature of the gas are changing. Now in another special case, we can have a case where this temperature and pressure, these are two variables, and volume of the gas is not there. So whenever two variables are temperature and pressure, then let's how we deal with this entropy change. Means now we have to face a situation where pressure and temperature of the gas, these are changing, and we are not given the parameter for volume. So if volume parameter is not given, definitely it has to be converted into pressure and temperature terms. And you know it very well that pressure, volume, and temperature, all these three parameters of a gas, they are well interconnected with each other by means of ideal gas equation PV equal to RT. Correct? So suppose we are again dealing with 1 mole of gas, and for this 1 mole of gas, if in the initial state P1 is the pressure, V1 is the volume, and T1 is the temperature, means all these three are variable, then the expression for this initial state will be equal to P1 V1 equal to RT1. And similarly for this final state, if P2, V2, T2 are the pressure, volume, and temperature respectively, then in that case what will happen? P2 V2 will become equal to RT2. Now if we divide this P2 V2 upon RT2 with this P1 V1 upon RT1, so we will be having an expression for V2 by V1. Means by making use of these two relationships, it is quite easy to find an expression for V2 by V1. So V2 by V1 comes out to be what? P1 T2 and P2 T1 in the denominator. So we have this value of V2 V1, V2 by V1 in terms of P1 T2 divided by P2 T1. So now what we have to do, we have to substitute this value of V2 by V1 because V2 and V1 are not given to us. What we are given? We are only given temperature and pressure. Therefore, V2 and V1 terms in this equation number 43, we have to, or 42 for 1 mole we are talking about. So for this equation number 42, we have to substitute these values of V2 and V1. So let's see what happens when we substitute the values of V2 and V1 in equation number 42. So equation number 42 says delta S is equal to, correct, delta S is equal to Cv times of ln T2 by T1. We do not have to disturb, we do not have to change this T2 by T1 because T1 and T2, both of these temperature will be given for this case. Next is R, gas constant. Then again it is ln of what? V2 by V1. So ln V2 by V1 we can call it as ln of P1 T2 divided by P2 T1 because we have this expression for V2 by V1 in terms of P, pressure and temperatures. So suppose if we expand these two terms, because these two terms consist of product of two type of things. So when we expand this uh, product of terms in logarithm, then what will be happen? Delta S will be equal to Cv ln T2 by T1 plus first term will be equal to R ln T2 by T1 minus R times of this ln P2 by P1. Correct? So we have expanded this product into plus minus terms. Now we know that Cp minus Cv for 1 mole of gas is equal to R. Cp minus Cv is equal to R. So if we substitute Cp minus Cv equal to R, then the value of Cv plus R will be equal to Cp. So the first two terms in equation number 45, if we combine both of them, then these two terms are having common ln T2 by T1. So if we combine these two, then we will be having Cv plus R times ln T2 by T1. Is it or not? But Cv plus R is what? Cp. So this equation number 45 gets modified to the new simplified form in terms of equation 46. So in 46 we are having what? Delta S is equal to Cp ln T2 by T1 minus R ln P2 by P1. Now this is an expression for entropy change that is taking place during this temperature change and pressure change of the gas. Means if the temperature of the gas changes from T1 to T2, pressure of the gas changes from P1 to P2, then in that situation this delta S will be equal to Cp ln T2 by T1 minus R ln P2 by P1. So students, so this equation number 46, it holds good for 1 mole of gas. If we are having n number of mole of the gas, then definitely this number of mole will also be appearing with each of these two terms. So in that situation, your delta S will come out to be equal to n Cp ln T2 by T1 minus nR ln P2 by P1. Now from this above equations, means if we look into this equation number 47, so in this equation number 47 we are having an expression for entropy change. So during this entropy change, what happens? This entropy change for the change of the state of an ideal gas depends on initial and final pressures because P1 P2 they are appearing in this expression, and this is also appearing on initial and final temperatures of the gas. So delta S is what? N times Cp. Cp is what? heat capacity at constant pressure, ln T2 by T1 minus nr ln T2 by T1. Now we have two expressions. One expression is this equation number 43. So we have to make use of this entropy change expression whenever the variables are temperature and volume. But we have to make use of this equation 47 whenever we are having what? Temperature and pressure as the variable. So these expressions holds good for an ideal gas, because during the derivation of these we have made use of this concept of ideal gas equation P equal to nRT. So one numerical problem you can do. So you have to calculate the changes entropy that is accompanying the heating of 1 mole of helium gas assumed ideal. So students, in NET exam, definitely this thermodynamics part plays a very important role. So when we qualify this NET exam, so students, you are having my screen.
Yes, sir.
Yes, sir.
So what I am discussing, importance of this thermodynamics part. So this thermodynamic part has to play very important role in your NET exam. So in 2007-8, when we qualified this NET exam, so there were two papers. One was for pre, as well as one another paper was for main. Main was the written type, means we have to attempt questions on particular seats. So in pre as well as in mains. So in pre-exam, you can expect 15% of questions, means 15 to 20% of questions you can attempt if your thermodynamics part is very strong. And as far as main is concerned, so if my success in this exam is considered, then in case I do not know thermodynamics, then it would not be possible for me to qualify that exam, because maximum part in the second paper that I had attempted, so it belongs to this thermodynamics part. But dealing thermodynamics, this is quite tricky. Quite tricky means all these mathematical expressions, all these derivations should be on tips. Means if you know each and everything, how to derive, sometimes you also do not remember a particular relationship. Then in that situation, you should know the derivation in a shortcut way and within a fraction of seconds, not fraction of second, fraction of minute. Means within 30 seconds, you are having your expression in your hand. So it is not easy to remember, to learn all these thermodynamic relationships. And as far as my own uh, view is considered, so I do not believe on my remembering things, means what I have remembered, so I do not believe. So what I do, I try to drive these mathematical relations within 30 seconds, within 25 seconds, within 45 seconds. Once I am satisfied that no, I am correct, my remembrance was correct, then and only then I have to make use of these formulas. Otherwise, making use of wrong formula in physical chemistry, definitely you will be having zero. So what I advise to you, you should have a very good command how to drive these mathematical relationships within fraction of minutes. It should not be the time consuming. You got my message? So better to have more and more practices on thermodynamics, their derivations, numerical problems. When you would like to attempt numerical problem, then you have to think, you have to go through this statement of the problem very carefully. So now calculate the change in entropy that is accompanying the heating of 1 mole of helium gas, and assume it is ideal. It means that you are treating this helium gas as an ideal gas, and this is taking place temperature of 29 Kelvin to a temperature of 1000 Kelvin. One more important thing that I would like to make it very clear, in all thermodynamic relationships, we have to make use of absolute temperature. We have to make use of Kelvin scale temperatures. So T1, T2 you are given, and at constant pressure means pressure is constant to you. If pressure is constant to you, what will happen? If pressure is constant to you, then this expression P2 by P1 will be 0. Will it be 0 or not? In equation number 47. So second term will not be there. Then the entropy change will be what? NCP ln T2 by T1 only. Do you agree with me? Because at constant pressure, he is saying, it means that this second term contribution will be 0. We will be having only first term contribution towards entropy change, and that will be equal to NCP ln T2 by T1. If we are talking about 1 mole, definitely N will be 1. CP ln T2 by T1. It means that what is the value of CP? Value of CP is given. How we can calculate CP? CP is equal to CV plus R, and CV plus R is equal to what? 3 by 2 R. It is given there. 3 by 2 R, CV is given, plus R, it means 2.5 R. And the value of gas constant is what? 8.314 joule per Kelvin per mole, correct? And this is to be multiplied with log of this final temperature, means 1000 Kelvin divided by 298 Kelvin. And when you perform these calculations, then 25.17 joule per Kelvin per mole will be the entropy change. In objective type questions, what we do, we make this initial and final temperature in such a way that this log term becomes quite easy for calculation purpose. So you can expect such type of questions in your exam also. Definitely in competitive exams, these type of problems have to play an important role. Now another question is there, 1 mole of an ideal gas, this is heated from 100 Kelvin to 300 Kelvin, means we are having T1, T2. Ideal gas, definitely ideal gas means these expressions that we have discussed will be quite helpful. And calculate delta S if the volume is kept constant. Volume is kept constant means V1, V2 are constant. So T1, T2 we have given V1, V2 are constant. So suppose two variables are there, one is T1, T2, another is V1, V2. Definitely this equation we have to make use. So this equation number 43 we have to make use. If T1 and T2 are only the variables, V1 and V2 remains constant, this contribution from the second term will be 0. Only we will be having contribution from first term. And if we apply this formula, delta S will be equal to CV ln T2 by T1, because the second term in terms of volume that is disappeared. Why it is disappearing? Because volume is constant. So delta S will be equal to CV is 1.5 times 8.314 joule per Kelvin per mole, and this log of this 300 Kelvin divided by 100 Kelvin. So these type of temperatures you can expect in your competitive exam. 300 divided by 100 means 3, and ln3 you can calculate its value quite easily. ln3 is equal to what? You should remember what is the value of ln2, ln3, like that, correct? Now if pressure is taken as constant, so if pressure and temperature are two things, then definitely this equation number 47 will be quite helpful for us. So equation number 47 we apply, and pressure is constant, only the first term will be appearing like the previous example number 9. So we can calculate this entropy change if pressure is taken as constant. So all these things we have discussed. Now if we modify these relationships, equation number means 47 and one is equation number 43. So if we are talking about at constant volume, means isochoric processes. For isochoric processes, this expression will be equal to delta is equal to NCBT2 by T1. So that we have discussed here. If we have isothermal process, so during an isothermal process, the entropy change will be denoted by delta S T. T means temperature is constant. So if temperature is constant, so we will be having this expression for entropy change R ln V2 by V1. This will be equal to minus R ln P2 by P1, and you can write it also as R ln P1 by P2. So minus sign is adjusted within the log itself. So these are some simplified or more specific relationships that holds good for an isothermal process. So if someone asks you calculate the entropy change during the isothermal process, so definitely we have to make use which of these relationships we have to choose whether volume is changing, whether pressure is changing. If volume is changing, then delta ST will be equal to R ln B2 by V1. And if pressure is changing, then it will be minus R ln P2 by P1. And if you want to convert this into positive sign, then R ln P1 by P2. So this equation number 48, this is nothing but this is the special case of these equations that we have discussed later. Means for equation number 47 and one another equation. So if we are talking of isobaric process is for which there is no change in pressure, P1, P2 remain same. So expression for this delta S at constant pressure will be equal to Cp ln P2 by T1. So you have to remember these relationships, equation number 47 and equation number this 43. All these relationships will be quite helpful in finding out the expression for these special cases. One is isothermal processes, another is isobaric processes. This is isobaric processes, means during this process no change in volume takes place. So this relationship delta S will be equal to Cv ln T2 by T1. So students, we have now derived so many relationships depending on the nature of the process, whether it is isothermal, isobaric, isochoric, whether temperature pressures are changing, whether temperature volumes are changing. So a variety of mathematical expressions we are having, and which relationship you have to make use, only it depends on your choice, it depends on your system, it depends on your process, whether it is taking place at constant temperature, constant volume, constant pressure, like that. So example number 11, 1 mole of an ideal gas, this is expanding reversibly from a volume of 10 decimeter cube and a temperature of 298 Kelvin to a volume of 20. Means volume V1 is 10 decimeter cube, V2 is 20 decimeter cube. So V1, V2, T1, T2, all these things are to be taken in such units that units are common for all these. Volume is always to be taken like that. If it is one term is in decimeter, another definitely it should be in decimeter. Temperature is in Kelvin, another temperature should also be in Kelvin. And you have to calculate this entropy change. So this and each and every numerical problem that we are discussing, and it is clearly mentioned that this is the case for an ideal gas, because for non-ideal gas it would not be possible to calculate all these things like that, because non-ideal gas, this P1 V1 equal to P2 V2, like these things does not hold good. So delta S expression for this, because volume and temperature, these are two variables, so this expression we are making use. If 1 mole of gas is there and is not appearing there in this expression for delta S, so this value comes out to be equal to 3.57. Now, next is if the gas in the above example expands reversibly and adiabatically, what would be the value of delta S for this process? So for reversible adiabatic process, during adiabatic process, what happens? No heat exchange is allowed. No heat exchange is allowed. It means Q reversible will be 0. If Q reversible is 0, then what will happen? The change in entropy of the system will be 0. Why it will be 0? Students, I want to answer from your side. If Q reversible is 0, then why delta S will become automatically 0?
क्योंकि सर डेल्टा एस इक्वल्स टू क्यू रिवर्सिबल डिवाइडेड बाय टी, तो क्यू रिवर्सिबल हमारा जीरो है तो डेल्टा
Yes,
एस हमारा
fine.
जीरो ही होगा.
Thank you. So, because in the mathematical expression of delta S itself, it is Q reversible divided by T. If Q reversible is 0, then everything will be 0. No entropy change has to take place. Means for an adiabatic process that is taking place, Q reversible is 0. So in that exam, this question plays an important role. So expression statement will be like that: for a reversible adiabatic process. For a reversible adiabatic process, delta S is always 0, delta S is always positive, delta S is always negative. So none of the above. So these type of statements you can face. So answer is hidden itself in there in the adiabatic process name. For adiabatic process, Q reversible is 0. Now another example, you are having 1 mole of an ideal gas, it expands reversibly from a temperature of 25 degrees and pressure of 1 atmosphere to a temperature, means two variables are temperature and pressure. Two variables are temperature and pressure, and temperature is given in degree centigrade, convert it into Kelvin scale. Then pressure, one pressure is what? 500 mmHg, and another pressure is 1 atmosphere. So all these pressure units, one is given in atmosphere, another is given in mmHg. तो 1 atmosphere pressure क्या होता है, वो 760 mmHg होता है. 1 atmosphere pressure क्या होता है, 760 mmHg. So you have to convert this 1 atmosphere pressure into 760 mmHg. Then you have to make use of this expression or mathematical formula for entropy change. ये जो एंट्रोपी चेंज है, ये डेल्टा है Cp ln T2 by T1 प्लस R ln P2 by P1. ये अभी हमने ड्राइव किया था, इसको यूज करना है. Cp माइनस Cv R होता है, तो Cp की वैल्यू आप इसमें Cv अगर गिवन है आपको, यू कैन कैलकुलेट इट. तो 2.5 टाइम्स R. R जो गैस कांस्टेंट है, ये भी आपको जुडिशियली डिसाइड करना है कि गैस कांस्टेंट की कौन सी यूनिट्स आपको यूज करनी है. सो इन दिस what type of temperature we are using? We are using Kelvin scale temperature, correct? So for Kelvin scale temperature, the units of this gas constant R is 8.314 joule per Kelvin per mole, correct? We are on the molar basis, we are on the Kelvin scale, therefore the units of this R gas constant will be equal to 8.314. Students, किसी को कोई doubt है? जो एंट्रोपी वाला है, lots of time I have consumed in order to explain the concept of entropy. What are the various mathematical expressions for calculation of entropy? Which mathematical expression you have to make use while doing the calculations, depending on the type of process that is happening. So this type of इस वाले न्यूमेरिकल में ये जो ट्रिक था थोड़ा सा कि 1 atmosphere pressure और 500 mmHg जो प्रेशर है, both units should be same. Because you always keep in your mind that same type of things can be added, same type of things can be divided, same type of things can be subtracted. Clear? If one thing is in mmHg, another thing is 1 atmosphere, then what is the meaning of dividing this atmosphere with mmHg? No. Units of both of these terms should be same. So the message that I have given to you that similar type of things can be added, similar type of things can be divided, similar type of things can be subtracted, correct? So this concept you have to keep in your mind always while performing numerical problems. Clear? So today I have to explain only that much. So please go through some other examples you may find in certain textbooks in the calculation of entropy and all these things. तो अगर किसी को कोई डाउट है then
Sir?
class is
Sir,
just wait a minute.